Welcome to part 8 of Origin of the Elements, and this is episode 2 in our discussion of how we build elements heavier than iron. So, last time we found out a way of making elements heavier than iron using neutron capture. So instead of trying to fuse increasingly highly charged nuclei, we add neutrons. Neutron capture makes heavier isotopes, and then beta decay turns the neutrons into protons, moving them to a new element. And depending on which happens faster, we can get two very different pathways. If the beta decay can happen between neutron captures, then we get the slow neutron capture process, or S process, which stays relatively close to the value of stability. If neutrons are captured faster than beta decay can occur, then we get the rapid neutron capture process, or R process, which drives nuclei far out into the neutron-rich side. So we have two ways of building up elements heavier than iron. At the end of the last episode, I left you with two questions. Where in the universe do these processes actually happen? And if we can't actually watch nuclei capturing neutrons, how do we know that any of this is really happening? Fortunately, neutron capture leaves us some fingerprints. And our first fingerprint comes from a rather wonderful bit of nuclear physics. Magic numbers. You may remember from atomic physics that electrons occupy shells, and the atoms with completely filled shells are particularly stable, so think noble gases. Something rather similar happens inside a nucleus. Protons and neutrons also occupy energy levels, and certain numbers correspond to closed or filled shells. These are called the magic numbers. The full set of nuclear magic numbers is 2, 8, 20, 28, 50, 82, and 126. For the heavy element neutron capture processes, we're interested in the higher numbers. So the important neutron magic numbers are 28, 50, 82, and 126. When a nucleus has one of these closed neutron shells, it is particularly stable. And importantly for us, it has a relatively small probability of capturing another neutron. We describe the probability using something called the neutron capture cross-section. When a nucleus reaches one of these closed neutron shells, its probability of capturing another neutron becomes relatively small. So instead of readily capturing another neutron and continuing along the neutron capture pathway, nuclei tend to remain at these closed shell configurations. Over time, that produces an enhanced abundance of nuclei associated with the magic neutron number. We often describe these closed shells as bottlenecks in the neutron capture nucleosynthesis, and that means that the nuclear structure itself should leave a fingerprint in the abundance patterns. But exactly where that fingerprint appears depends on the path we're taking through the isotope map. So let's start with the S process. Now let's start by putting this onto the nuclear landscape. We have our value of stability here. In this case, I've got protons on the horizontal axis and neutrons on the vertical axis. Here we can see the stable elements are in black. We care about the blue side, that's where it's neutron rich. As neutron capture and beta decay move us towards heavy elements, the S process eventually comes across a closed neutron shell. So we've got something that it's adding neutrons, but it's decaying. It's adding neutrons, it's decaying. But eventually it's going to get to a point where it meets the fact that it has 50 neutrons in a shell, and it's going to be right about here. Because that closed shell has a very small probability of capturing another neutron, it tends to stay there and not add extra neutrons. And that results in an enhanced abundance of the nuclei associated with that closed shell. So let's move along. We've got something else that's been adding things, and now we get to the next number, which is 82. And so what you're going to get is these nuclei here, where the number of neutrons is 82, it's filled the shell. It's very hard to add another neutron and keep following the S process path up here. And again at 126. So the magic numbers create a series of bottlenecks along the S process path. And because the S process stays close to the value of stability, these bottlenecks occur in nuclei that are themselves close to stability. So rather than producing a smooth distribution of heavy nuclei, the S process should leave us with peaks in the abundance pattern associated with these closed shells at 50, 80, and 126 neutrons. Now let's look at this diagram from the point of view of the R process. The R process does not stay close to the valley of stability. It travels much further out on the neutron-rich side. So you are going to build things that start here and you keep adding neutrons, and then when you get here, it gets stuck. But that's going to give you then a very different pattern coming back. And we're going to look at that in a little more detail. So here, just zooming in, if we're talking about the S process, we're going to have elements that are going to be about here. If we're talking about the R process, it's going to have something that builds up to a lot of protons here, and then it will beta decay back to here. So it will make a different set of stable nuclei. So now let's look at the R process in more detail. But before we do that, let me orient you to this figure. This again has plotted protons versus neutrons. However, this is more like those detailed isotope maps where it is increasing neutrons on the x-axis and increasing protons on the y-axis. Also, this figure is not showing the entire stability landscape. So this is actually only half the valley. The bottom of the valley, the valley of stability, is this black line here. And actually, there should be a whole bunch more elements on this side, but it's only showing you the neutron-rich side. So because that's what we care about with neutron capture. And so what we're seeing on this side is the stuff that's got lots and lots of neutrons. The color scale here is given by basically the half-life for beta decay. The half-life is a measure of how unstable something is. So the longer the half-life, the more stable it is. So these are all unstable, but they're getting more unstable as you head away from the valley of stability, unsurprisingly. It also gives us this direction for how the neutron capture and beta decay is working. So neutron capture moves the nucleus to the right, and beta decay moves it up and to the left. So let's think about the R process. The enormous supply of neutrons drives the R process far out onto the neutron-rich side, well away from the valley of stability. So we've got stable stuff, and you're going to have something that you're adding lots and lots of neutrons, so it's moving out in this direction. So let's consider that we've got something that starts here, and we start adding neutrons, and we're adding neutrons, and then we get to here where n equals 82. We've added enough neutrons that it has 82, and it has a closed neutron shell. And you can actually see that something interesting happens here with the closed shell. So this pink line is actually showing you where you get nuclei related to the R process. So what we get is as a bottleneck at this point. We've got something that starts over here and ends up at 82, but it's also something over here. You keep adding neutron, it's going to end up here, and it can't get past it. The cross-section is so small that we can't keep adding neutrons. So the R process encounters this bottleneck, or what we sometimes call a waiting point. The R process material doesn't just keep going, it stays there, and we end up with an abundance enhancement associated with this n equals 82 shell. But these are not stable elements. So if you've got something that's here, it's going to beta decay back to valley of stability, and you're going to end up with a specific nucleus or set of nuclei related to that pathway. Now notice that it's not the same nuclei that we're encountering with n equals 82 for the slow process and the rapid process. For the slow process, it's always going to be very close to the valley of stability, so it might be here and end up here, but you can have something that ends up all the way down here in the rapid process where you've added lots and lots of neutrons, and now the beta decay is going to bring it down over here. And so we have to worry about this whole process of what elements and what isotopes do we get from these two different processes. So let's take a specific example. And we're going to look at this cadmium. Cadmium is an element that has 48 protons. And if it's at 130, we've added enough neutrons that it has 82. It's got a full shell. But this is not stable. And so it's going to beta decay. So this is where it's got a full shell, it's got all the neutrons it needs. And so now it's going to start divesting of those neutrons and converting them into protons. So the first thing it does is it ejects a beta particle and makes indium. Still the same mass, more protons. And then you're going to do that again and make tin. And then you can do it again and make antimony. And then you can do it again. And finally, you get something stable, and you've got tellurium. And this is a stable isotope of tellurium. Notice that these do not have full shells of neutrons. The closed shell requires it to have 82, but you keep converting neutrons into protons. So these may actually also take a path this way and then follow another path back to stability. And so it can get very complicated. So now we can finally look at the abundance patterns and see the fingerprints that we've been predicting through looking at these processes. So here we've got on the horizontal axis the atomic mass number, and here we've got the log of the abundance relative to having 1 million silicon atoms. Okay, this doesn't really break it out into isotopes. What we're seeing is it's definitely not smooth. We've got lots and lots more hydrogen and helium, and it drops off, but it doesn't drop off just simply. You've got a peak here around making iron, and you've got some peaks here that are shown as being S or R process. So let's start with the S process. Because the S process stays close to the valley of stability, when it encounters one of the magic numbers, it encounters a relatively small number of nuclei close to stability. And so what we get is the S process will tend to produce a relatively narrow, well-defined abundant peak. So you can see here we've got a peak here that's very narrow. It's going to make this mostly this because it's very, very close to the value of stability. Same with this peak here and this little peak here. On the other hand, if we look at the R process, this hump here and this hump here, they're broader. And we know why. During the R process, we encounter the magic neutron numbers much farther away from the value of stability on the neutron-rich side. And so it reaches, for example, with fewer protons. So you can see here, this one would have started out with the same number of neutrons as this one, but it's converted more of them to protons because it started further away in stability. What we get is also that because there are multiple pathways it can take as you're converting those neutrons into protons and changing what's stable and what's not, you get a wider distribution of possible elements through this path. So the R process peaks are generally broader, and that is because they don't just follow this one path to the stable nucleus. So different neutron-rich progenitors can feed into a range of final nuclei, and the processes during the decay back to stability can also redistribute this material into slightly different isotopes. So instead of a relatively sharp pileup like we see with the S process, the R process produces these broader peaks, abundances due to the magic numbers. So this is the really satisfying part. We started with some fairly abstract nuclear physics. Neutron capture, beta decay, closed nuclear shells, and magic numbers. But that physics leaves us patterns. The locations and shapes of these abundance peaks are a fingerprint of the process that made the heavy elements. So this is one way we know that a single neutron capture isn't enough. We need both the slow process and the rapid process to explain the abundance patterns we actually observe. And that brings us to the next question. Where in the universe can these two different neutron capture environments actually occur? So where do these elements actually come from? So now instead of this being the mass number, it's the atomic number. You see it's a fairly similar kind of distribution, and it's still just a relative abundance. But what we can see is the very lightest elements are mostly from the Big Bang. Yes, we're making elements inside stars, including helium, but it's negligible compared to what was made during the Big Bang. Then you've got the relatively low mass elements that are largely made in high mass stars. These are actually largely formed by the alpha process, where we're sticking heliums together and bigger elements. And then we've got the iron peak, which are largely coming from low mass binary stars that explode. And then once we get past the iron group elements, it's pretty much all from neutron capture, and that means massive stars that explode as supernovae, giant stars that do the S process, and also binary mergers, which we'll be getting onto in a little while. So here's another way to visualize that same story using the periodic table. This is Jennifer Johnson's representation of the origin of the elements. Notice that there are many boxes that have more than one color. That's because many elements don't have a single nucleosynthetic origin. So if we look at carbon, for instance, most of it came from low-mass dying stars, with a small number from high-mass stars that explode. On the other hand, if we come down to palladium, we've got merging neutron stars, and low-mass stars are not exploding stars. Different processes can contribute to the abundances of the same element. In the heavier elements in particular, we can see contributions from both S process and R process. So when we talk about an S process element or an R process element, that doesn't necessarily mean that that element only has one possible origin. Here's the same basic information displayed slightly differently. The visual encoding is different, but again, we can see that there are many elements that have contributions from more than one nucleosynthetic source. But there's one little box on this diagram that I want to draw your attention to. Right here, element 43, technetium. Look how it's classified. Human synthesis, no stable isotopes. That second part is really important. Technetium has no stable isotopes. So any technetium that exists is radioactive and will eventually decay away. The reason it's marked here as human synthesis is that technetium was the first element to be produced artificially. And that's where it got its name from. But it doesn't mean technetium exists only because humans make it. In fact, technetium gives us one of the most beautiful pieces of evidence that nucleosynthesis is actually happening inside stars. Think about the problems we've been discussing. If I find something like barium in the atmosphere of a star, I don't necessarily know that that star made the barium. It could have been present in the material from which the star was formed. But technetium is different. It has no stable isotopes, and all of the isotopes eventually decay. What does that mean if we find technetium in the atmosphere of a star? It means that it must have been produced recently enough that it hasn't had time to decay away. And in 1952, Paul Merrill discovered technetium in S-type stars. That was direct observational evidence that these stars were making new atomic nuclei. And as we'll see, it provides a remarkable piece of evidence for the S process. Remember again that technetium has no stable isotopes. Here we can see all of its different isotopes and their many half-lives, and they vary from a few hours to millions of years. What does this mean, though? If we compare the timescale, a few million years at the longest, to the lifetime of an evolved star, these stars are vastly older than the longest-lived technetium isotope. So any technetium that's present in the material from which the star originally formed would have disappeared long ago. And yet, we found it in the atmospheres of stars. So where did it come from? It can't be primordial. It must have been created recently. And that's what makes technetium so important. It's effectively a radioactive clock. Its presence tells us that nucleosynthesis has occurred recently enough that technetium hasn't had time to decay away yet. And there's another important part of this story. The nucleosynthesis happens deep inside the star, but the technetium was detected in the star's atmosphere. So, newly synthesized material must also have been mixed from the interior up to the surface. So technetium gives us remarkable direct evidence that these evolved stars are actively producing heavy nuclei and dredging newly synthesized material up where we can observe it. And the process responsible for producing those heavy nuclei is the S process. So now we have evidence that the S process is really happening in evolved stars. But we've been taking something rather important for granted. To capture neutrons, we have to have a source of neutrons. So where are they coming from? For these low-mass stars, the primary source of neutrons is actually from having carbon-13 that then fuses with helium and makes oxygen-16, which is the most common isotope, and ejects a neutron. There are many different pathways this could take. Here I'm showing the way we normally note this in nuclear physics. So we have something that starts out as carbon-13. We add an alpha particle, that's what a helium nucleus is. We eject a neutron and we get oxygen-16. So it's saying the same thing. If you remember in one of our early videos, we talked about the CNO cycle. So we're making carbon-13 and we may be able to have it fuse with helium before it takes another hydrogen in the CNO cycle to make nitrogen. There's another important pathway, but this only happens for the higher mass of these low mass stars. So AGB stars are basically between about 1 and 8 solar masses, much more massive than that, and they're going to start to be stars that explode. These ones don't. But the higher mass end in the 4 to 8 solar mass range can also do these higher temperature reactions where you've got a neon and you add an alpha particle, a helium, and it makes magnesium-25 and a neutron. Again, in that notation, neon plus an alpha particle ejects a neutron and gives us our magnesium. So what we've got is that the low mass stars have a source of neutrons. The higher mass within these lower mass stars, they have access to more neutrons. So what about the R process? Where do its neutrons come from? And here the problem is rather different. For the S process, we could identify particular nuclear reactions inside stars that release neutrons. But remember what the R process has to do. It has to bombard nuclei with neutrons so rapidly that they capture another neutron and another and another and another before they have time to beta decay. So we don't just need a source of occasional release of neutrons, we need an environment containing an enormous abundance of free neutrons. Neutron capture has to occur faster than beta decay. So that requires conditions far more extreme than the gentle neutron production that we saw in the AGB stars. And so we need to find somewhere that has lots and lots of neutrons, and it's going to come from and give us rapid energetic events. And so we know the abundance pattern for our process must happen, but we need to figure out where in the universe it actually happens. So where have we got to? We started this episode with two questions. How do we know that neutron capture nucleosynthesis actually happens? And where in the universe does it happen? We found several fingerprints. The magic neutron numbers create bottlenecks, and those bottlenecks leave recognizable peaks in the abundance of heavy elements. And the different paths taken by the S process and the R process leave different abundance patterns. For the S process, we can go further. We find technetium in evolved stars. Because technetium has no stable isotopes, its presence tells us that nucleosynthesis has happened relatively recently inside those stars. And we know that those stars can provide neutrons. Carbon-13 and neon-22 give us neutron sources under conditions found inside these stars. So the pieces of the S process story fit together nicely. But the R process leaves us with a much bigger problem. We know it happens because we can see its fingerprints in the abundance pattern. We know what it requires. Neutrons have to be captured extraordinarily rapidly before these extremely neutron-rich nuclei have time to decay. So, somewhere in the universe, nature has to create an environment with an enormous neutron supply. But where? What kind of astrophysical event could possibly produce conditions that extreme? For a long time, this was one of the major unanswered questions in nucleosynthesis. And then the universe gave us a spectacular clue, which we'll come back to in our next episode.